right? And pressure, 1 kilogram of that thing occupies this space. So I guess that there's going to be a change in the volume, right? As we could possibly see here. I hope this question is actually correct and all of that. Let's see here. It says that what is the energy supplied during this change? How do we go about finding that energy, by the way? So we want to find the energy supplied um, in this change. So obviously that energy that we're talking about here is um, the heat energy. I would assume. Energy supplied to produce this change. Let me just see if I can bring up this question quickly. Give me a second here. Um, but think about it in the meantime while I try to bring it up. Okay, okay. All right. So in order for us to find that heat that is supplied, right, to the system, because because we're converting water, right, to steam, then it means that, let me see the question again, because I think I left out a little bit of information related to this question. Did I leave out some information? I think I did, right? Because what we have to understand is that we're basically converting water into steam. And we know that at 100 degrees, that's when, you would possibly find steam being located, right? Or, that change of phase occurring. So if I want to find out the amount of energy that was used to essentially convert that amount of water to steam, then I would have to use the whole aspect of um, but using this equation that says Q, which is talking about the energy, is equal to the mass of the water times the latent heat of vaporization, right? So this is what I would have to use to find out the amount of energy that was required to change that state of water into steam, right? So I would have to use this equation. But let me know if you guys understand what we're doing here,
Yes, sir.
right? So the question had given us the latent heat of vaporization, right? And we know the mass, which is 1 kilogram. So by way of just putting that information here, so 1 kg times 2.26 times 10 to the 6 joules per kilogram, then we should get the amount of energy, which is the heat that was supplied to the system. So in this case, that is going to be 2.2 6 times 10 to the 6 joules. All right. So having said that, we know the heat energy, right? Now the question would go on to say that find the work done against the atmosphere rather. So let's see here. You want to find the work done against the atmosphere. All right. So chances are they gave us the pressure, right? They gave us the volume difference, right? So in this case, we're going to use the equation that says work is equal to pressure times the change in volume, right? Because there's a change in volume, and we know the pressure that is supplied to the system. So we can use that information to find out the amount of work that was done against the atmosphere. In this case, I expect that the answer should be a negative work, because once you're doing work against the atmosphere, in this case, the work is going to be negative, right? So let's look at it now. So work is equal to the pressure, which is 1.01 times 10 to the 5 times the difference between the pressure. Now, mind you that this is my final pressure. My bad. My final volume, rather. Change in volume, I should say. So let me say that again. So the work is equal to the pressure, which we know is 1.01 times 10 to the 5 times the change in the volume. Now, typically we would say final minus initial volume, right? So we must identify that this is the final amount, this was the initial amount, right? So we have 1.01 times 10 to the minus 3 as my final, minus 1.67. All right, let me just confirm. All right, let me just check something here. So, all right, I think there is, I don't know, this book is really not good. I mean, it just keeps making other errors, you know, because when I look back at the working out here, this thing is not, this is supposed to be positive and not negative, right? So there's some issues with that book. So let's correct that then. Let's correct that, because there's some issues with that book. I think there's some issues with the book. Right? So I believe this is what it's supposed to be. Unless I don't know what's up with them. I don't know what they're doing. I really don't know. Like, you know. They have so many errors. Like, so that's the final. This is the initial. Okay. Yeah. Somebody go ahead and work out that for me now and see what we're getting. Right? I'm totally against this in a sense. I don't know what's going on with this question mainly, but let's just work it out and see what we're gonna get here. Right? So we're essentially multiplying this pressure by the difference in the volume, right? I should, because I'm doing work against the atmosphere, does that mean that my work is going to be positive? Does it mean that's going to be negative? Let's see. If you're doing work against the environment, that means that your gas is expanding, right? So the work, yeah, it should pans out to give us a negative value, but based on this calculation here, it's not going to give us a negative value, right? It's not going to give us a negative value. Go ahead and just work this out for me and see what we're getting. We should be getting a negative value, but it's not going to give us a negative value. But at the end of the day, we must understand that because we're doing work against the environment, it's going to be negative. All right, so Rihanna said that she got that the work is equal to minus um, 660, well, not 600, 168,000 670. Did I get that correct? Yes, joules. Can somebody else confirm and let me know if that's what you're getting? Why am I getting what did I do here? Let me just check again. Why am I not getting that? When you guys work out the volume, the difference in the volume, what value did you guys get? No man, how did you get that? Remember now that the final volume is 1.01 times 10 to the minus 3, right? So yeah, well, okay. So let me just do this again. So 1.01 e to the third minus 1.67 is supposed to get that the change in volume is supposed to be um 1008.33, and then you would multiply that now by the partition. You see it's positive 3, because remember I said that there's a problem with the question. I'm going to show you the question. I'm going to show you the question. Right, there's an issue with the question based on what I've seen here. Right, so this is the question. Right, so here's the question right here. Right, in this they gave us that the volume is 10 to the minus 3. All right, But as soon as you reach down to the calculation part, you realize that you're not seeing 10 to the minus 3, you're seeing 10 to the positive 3, right? So there's something obviously going on right here. You see what I mean? If I'm doing work against, yeah, if I'm doing work against the environment, it means to me that the gas is expanding. All right. So I would expect that my volume at the end of the day should be of a greater value. But let me just see here. Right. It's yeah. So my answer, right, is the answer I'm getting is 101, right? 841,330 joules minus. So that is the work based on my calculation here. This is the work that I'm getting when I do my calculation, right? So I don't know. So let's check and see if that's what you're now getting if we consider that the volume is such. All right, good. It's going to be negative because you're doing work against the environment. All right. The question continues to say that we should calculate the increase in the internal energy. Now, whenever we are trying to find the internal energy, first we must understand that the internal energy is the sum of the heat supplied to the system plus the work done or by the gas mainly. So I will just have to use my first law of thermodynamics equation. That's what I would just need to use to find out what would be that total internal energy at the end of the day. So let's go ahead and see if we can do that. So, change in internal energy is equal to Q, which is the heat supplied, plus the work, right? So let's go ahead and now put in the values that we know. We know that the heat supplied is 2.26 times 10 to the 6 joules minus this amount. Now, we're obviously going to get a negative value. What this is going to just tell us is that our system is losing heat. So that minus sign is just going to show that the system is losing heat. So we should be getting minus 99,581,330. Exactly. Right? That is what I'm getting here now. Well, let me just go back to the question. But before, let's see. It says that we should find the increase in the potential energy of the molecules. All right, let's see how we're going to do that now. Increase in the potential energy. So, increase the potential energy. Because what you have to understand is that whenever there's a change in state, right, there is not an increase in the potential in the kinetic energy because there's no increase in temperature, right? However, there will be an increase in the potential energy. Let's see what they did as it pertains to this. right? Um, okay. So pretty much they're saying that, you know, at a change of state, there is no change in temperature, which is correct. And it says that all the energy supplied is used to increase the potential energy of the molecules and not their kinetic energy, as I would have kind of made allusion to. So, based on this, well, we're not working with their answers, right? Because I don't know what's happening with their answers. I'm gonna look back at the question and see if there's anything that probably we did wrong. But it says that therefore the increase in the potential energy of the molecules would be the same as the internal energy, right? But let me just check something here. All right. I think we we I would say we kind of did something. I wouldn't say wrong, but what we must understand here. Let's look back at the question. They gave us the amount of steam that was occupied, which is basically um your final volume, right? Because remember now, you know, if you're heating up the water and so forth, and you reach to the steam is like the product. So at the end right here, this is the volume of steam that is produced. Now this so-called would have been the volume of the water. So what they did here is correct, right? Providing that we know that the volume was 10 to the 3, right? So this is the correct way of writing it out. So we made an error right there, right? So, and if it makes sense to you, let me know, because what you have to understand, if they gave you the volume of the steam, remember, so the steam is the final thing. So that would have been your final volume, right? And of course, the other would be the initial um, volume of the water. You see what I say?
Yeah.
Yes? No?
Sir, if you look at the question, you see that they assigned the negative sign to the work done against the atmosphere when they work in the increase in internal energy.
Say that last part again for me.
I'm saying, sir, they assigned the negative sign to the
Mm-hmm.
work done against the atmosphere when they were working the internal energy.
Mm-hmm. Yes, yes, because we said that, you know, we said that the work done against the atmosphere uh should be negative, right? Should be negative. See that you're doing work against the atmosphere, it should be negative. But what I was just making reference to is the change in volume, right? Because they gave us this volume, which is the 1.67 as the volume of the steam, right? That is basically our final volume, right? And this right here, this 1.04 times 10 to the 3 would have been our initial volume. But for some reason, I think that it's supposed to be minus 3, because remember now, if you're
But
doing,
sir, they got the same answer we did the first time.
eh?
They got the same answer we did the first time.
What was that answer again?
It was 168,670.
When we had the minus,
That is, yes, sir. When we did when we used the -3.
yeah, so I'm thinking, you see, the reason why I'm thinking that this should have been not plus but minus is because of the fact that if you're doing work against um the environment, it means that your volume should be increasing. You understand? That's how I'm seeing it, right? The volume, because in this case, the gas is expanding, right? So I would expect that the initial volume should have been lower than the final volume. Let me just check something here. So give me a second. Okay, so you see it now. So it's obviously a typographical error, right? Because when I work out this with the minus, as you would have said, when I work it out with the -3, we get in this number, which is basically 163,000, so forth and so forth. So I see what you're saying now, right? I get exactly what you're saying. Right? So it's obviously a typographical error. So this is still minus. It's supposed to be minus because of the fact that you are doing work against the environment, which means that your gas is expanding because the gas is expanding and pushing it, pushing up the environment and all of that kind of thing. So the initial volume is going to be lower and the final volume should be higher. So when we work this out back now with the -3, we're seeing that it's going to give us what we actually want, right? Which is this value, right? So yeah. So thanks for that though. So basically we have to go back and probably work out the last part of this question. Well, from the work, where would we have to work out? We have to work out from here, so right? We have to work out back from here, so. So let's just make the correction here. So that was just an issue on their part, right? So you see, not at all times the things in the book will be, there are errors there as well. So make us see what I want to know. So clearly W is equal to P times change in volume. P is 0.1 times 10 to the 5 times my final volume, which is 1.67 minus my 1.01 times 10 to the -3 meters per second. When we do all of this here, so now it clearly shows us that this thing is going to be 168,564.96, and this is joules, which we can write it as 1.68 times 10 to the fifth joule. So this is the work. Well, as we said, it's a minus because of the fact that you're doing work against the environment. In a sense, you're losing heat, right? Or you're losing some amount of the overall internal energy. So if we go back now to correct the internal energy here, right? Internal energy is the heat plus the work that was done. The heat is 2.2 times 10 to the 6 minus the work here, which is 1.68 times 10 to the fifth. So 2.26 e to the 6 minus this answer, right? We should be getting that the internal energy is going to now be, this is the resulting internal energy, going to be 2091.4 joules, right? So this amount of energy that is remaining, right? That is the energy now that would basically be the potential energy that the molecules would have, because that's the overall energy that is remained in the system. And remember, we said that in the process of a phase change, there is no, what we call it, no increase in the temperature, right? Which means that there will be no energy going towards the overall, what do you call it, the overall kinetic energy, right? It will be going towards the potential energy, meaning that, particles are moving further apart from each other, so there's no an increase in the potential energy and so on. All right? And I think this was the answer that they got. Well, I don't know what's happening here. When we do subtract that,
I got the 2.09 times 10 to the 6, sir.
You got the negative 6?
6, sir, not negative 6.
Oh, well, 6, yeah. So let me just check again. So I have 2.6, 2 e to the 6 minus 1 point, we have less than a minute, so we have to restart. All right, yeah. So maybe I had something done incorrectly. So it is basically what is in the book, right? So it's 2.09, 6 times 10 to the, yeah. So this is the answer. I'll restart the session. Okay. Now I think we're back up to our full capacity in terms of the amount that was here, so we can possibly resume. Now, whenever we're dealing with thermodynamics, right, there are some type of thermal processes that takes place, right? And we have to become familiar with these terminologies or when those processes are taking place. Now, from time to time, whenever whenever we have a particular gas, for the most part, there are times when we can have certain things that is constant, such as maybe the volume, the pressure, the temperature, so on. When those things happen, right, it goes through a particular process, and we're going to look at how it looks from a graphical standpoint when there is constant pressure and what happens during the whole constant pressure scenario and so forth, right? So these are the four main type of thermal processes. We have what we call the isobaric process, and that is simply when our pressure is constant, right? We have the isochoric process. There's another terminology that we use for that. We can say the isovolumetric process as well. That is just when our volume is constant, so the volume of the gas is constant. We have what we call the isothermal process. That is just simply when the temperature of the gases remain constant. We have what we call the adiabatic or something of that nature process, right? That is simply when there is no heat energy added or subtracted from the system. In most cases, they might not tell you when it's an adiabatic scenario, but they can tell you that the thing is insulated. So if you see a question that says that the thing is insulated, then it means that no heat can be added or can be subtracted from the system. All right. So please ensure that you understand these terminologies, or you can look at a question to understand whether it will be an isothermal, isochromic, isobaric, or adiabatic. I think that's how it's pronounced. If you can pronounce it better for me, let me know it is pronounced. This one right here. Rihanna, how do you pronounce this? Adiabatic.
Adiabatic, sir.
Yeah, something of that nature. Right? As long as you remember, then that's fine. So those are the four main thermal processes, and we're going to see how we can use these things on a graph, or how it looks on a graph mainly, and so on. Once you're finished taking off that, just let me know so I can just proceed. So if we look back at the question that we got, just now, what was it that was constant?
Temperature, sir.
Okay, temperature. But it seemed as though the pressure was constant as well, to some degree.
And the pressure too.
Yeah. I don't know if generally we will have those two scenarios whenever we look at it, but I will show you what it looks like on the graph once you're through taking off this information. All right, I think you guys are through with that now. All right. So as it relates to the isobaric process, remember we said that that is when the pressure is constant, right? So once you see, when you get a graph and you see that there's a, constant pressure on your graph, basically, right? Then that just shows that this is going to be an isobaric process. So, Rihanna, I think this is the question that we looked at would be isobaric in a sense, right? So there's the possibility that, well, I don't know, maybe it can be isothermal at the same time, but let's not pressure it, right? But for this part, whenever you see something like this on a graphical standpoint, right, then you expect that from here to here you would have constant pressure. You know what I mean? So the pressure does not change. So quite often these are the type of graphs you will get related to thermodynamics for the most part, where you will have pressure on this axis and volume on the other axis here. I think by now we understand that if we go ahead and find the area underneath this graph, what would we basically find if we were to do that? What information can we get from the area of the graph? Hmm? Do we remember or we don't remember? Which one?
So is that something about work to find the work done?
Yes. So the area underneath the graph, the area underneath the graph, right, is used to find the work. work done. All right. In this regard, the work is going to be basically negative. The reason why it is negative is because the gas is expanding. Gas is expanding. And I think you can understand that because if the volume of the gas is moving from 2 to 4, then 2 to 5 rather, then that just simply goes to tell us that the gas is expanding, which means that the work is going to be negative because it's doing work against its environment to basically expand itself. Right? We understand that? Let me know. All right, no problem. So just remember those information, guys. That to see that once you see that the volume is increasing, it means that the gas is expanding, and when it is expanding, it is basically doing work against the environment. All right, and that's the isobaric expansion or isobaric process, as I would have made mention of already. All right, the isothermal now is when we say that the temperature is kept constant, right? So when that happens, if the temperature is kept constant, it means that there's no change in the internal energy, right? Let me say that again. So at constant temperature, it is telling us that the change in internal energy is going to equal to zero at constant temperature, right? Constant temperature. The internal energy is going to be zero. Mm-hmm. Yeah. So when that is equal to zero, so just remember that your internal energy is equal to zero. So if we consider in our first law equation, our first law of thermodynamics equation, we say that U is equal to Q plus the work, right? If U is equal to zero, right, then it means that Q plus W, right? Then we can just transpose this to say that the work that is done is going to be negative of the heat that is supplied to the system by way of just transposing this to make work become the subject. So work is going to equal to minus Q, right? So work that is done on the gas is equal to negative of the heat that is flowing into the gas during the whole process of isothermal, right? That is just what is happening here whenever you have this process of isothermal taking place. When you look at it from a graphical standpoint, this is mainly what it looks like when that process is taking place. that constant temperature, we're seeing that the pressure is decreasing with increased volume, right? So that's what is happening here. So once there's no increase in your pressure, in your temperature, right, we see where that the pressure is falling with increased volume, right? Yeah, so this is just essentially what is happening. So if you see a graph, if you see some part of your graph looking like this, then chances are it will be isothermal. If we wanted to find our pressure at certain points, then we could use our ideal gas equation that says PV is equal to nRT. So what if I know the volume, right? I know the mole and I want to find the pressure at a specific location, then I could use that equation to just kind of help me to find out certain things right there and then, right? So the adiabatic process now, as we would have stated that in that process, it does not, no heat is added or no heat enters the system, right? So as we said earlier, that is similar to when you have an insulated object for the most part. In this case, we're talking about an insulated cylinder. So in that process, right, it is how it works. It is similar to that of the isothermal graph. However, it's a more drastic, or it happens so quickly. So if you look at the graph right here, this one is for the isobaric, right? And you can see how the curve looks when compared to this one, right? It's more linear in a sense than the one that talks about isothermal. So you know, in some cases, you will have to probably identify what process it's going to be. So this one here, the first one, the one in black, that one, it's slightly curved in a sense. So that would speak to, when there's no heat added to the system. You follow me? Mm-hmm. Yeah. Now, if no heat is added to the system, what it tells us is that the work that is done, right, is going to be equal to the internal energy of the system. And that is when we're dealing with an adiabatic process, right? Since no heat is added, right, then it means that the work that is done here is going to be equal to my internal energy, or my internal energy is equal to the work that is done. And if I wanted to find the work that is done, I would have to find the area underneath the graph. When I say the area underneath the graph, I mean all of this region here. You would have to find the area underneath the graph to essentially find out what would be that overall work that is done, unless they state it to you, right? Any questions related to this? No, the last one here, which is the isochromic process, or in some case we call it the isovolumetric process, right? In that process, as the word suggests, isovolumetric, that is just when our volume, right, does not change, remains constant. So you would expect that if you're looking at it from a graphical standpoint and you see that a line going vertically downwards or upwards, then that just goes to show that your volume is kept constant, right? Yeah. So if the volume is kept constant, right? If the volume is kept constant, then what it means is that the internal energy is equal to the heat energy, right? Because remember now that if work is equal to pressure times change in volume, if my volume is 5 and the final volume is 5, then everything is going to be 0 in terms of my overall change in volume, right? So it means now that my work is going to be equal to 0. So what that also tells me now is that my change in internal energy is going to be equal to my heat energy. Hope you guys understand. Any comments there about? Are we all right with this information?
Yes, sir.
All right, great. So we have covered the main processes that occurs, or that we can talk about when it comes down to thermodynamics for the most part, right? So we have looked at isobaric. We said that that is when pressure is constant. We looked at isochromic, which is when our volume is constant. We looked at isothermal, when our temperature is constant. We look at adiabatic, which just speaks to when there's no heat added to the system. And when there's no heat added to the system, it means that our internal energy is equal to the work done on the system. So we must be able to can identify whenever we have an adiabatic scenario, right? We must understand the graph whenever we're looking at an isochromic or isovolumetric scenario. In that scenario, we said that the internal energy is going to be equal to the heat that is added to the system, mainly because our volume is constant. Because your volume is constant, it means that when you try to find the work using the whole concept to say that work is equal to pressure times change in volume, because your volume is constant, your final is going to be equal to your initial. When you subtract that, that's going to give you 0, so there's no work, right? So therefore, we said that the internal energy is equal to the heat energy. And it continues, you understand? So that's pretty much it. In the isobaric scenario, right, we must understand that the internal energy, right, is equal to the heat energy plus the work that is done, right? Once they tell you that heat is added to the system, then you must incorporate it in trying to find the overall internal energy. You know what I mean? So that is something that you probably can take note of. Or in some cases, we could say that the work is equal to the internal energy minus the heat supplied, right? So this is another way how they can say, maybe you know the internal energy, maybe you know the heat added, so you could just transpose this equation to find the work and so on. But let's look at maybe a question here. Where is that question? It's all the way down here. All right. So here's a question. It says that a gas expands from state A to B isobarically. It says as shown in figure such and such. Is positive work done on the gas or by the gas? That's the first question. What do you guys think? Hmm?
So your work is being done by the gas.
Yes. Work is being done by the gas. Any particular reason for you to say that?
Because it's expanding, so it's doing work on the atmosphere.
Precisely so. Expanded. Alright. Now question says how much work is being done during the process? How much work is being done during the process? Yeah, that would be the answer earlier, right? So in a sense, we find the area, right? So we know that area that seems, well, we don't even know what that is, but we know that area is possible length times width, right? Just imagine that that's a rectangle for the most part. So in this case, our length is going to be, I'm going to say 200. Now, as it pertains to the width now, it is 5 minus 3, or, well, my bad, 2 minus 5, which is going to give us 3. So in a sense, we're saying that, you know, 200 times 3 is going to give you 600 joules. But it's not just 600 joules, it's negative 600 joules, right? Because you're doing work against the system, right? So let's imagine now, we could consider it from another standpoint, just in a sense, just to just use the work formula and say pressure times change in volume. So 200 would be the pressure. The pressure is constant. And, well, as a matter of fact, let's correct ourselves here. It is kilopascals. So it is 200 kilopascals. So, that is something that you must always look out for, right? Because that is going to affect the answer now. So it's 200 kilopascals times the volume, which is basically 5 minus 2, right? So let's see now. So that is 200K times 3 is going to give us 600,000, right? Joules, minus 600,000 joules. Yeah. Yeah, man. Thanks, Patterson. So that's something to pay attention to. Right? That's something that we should probably pay attention to. I mean, if you guys understand. The question continues. It says that what becomes the internal energy of the gas? What becomes the internal energy of the gas? But wait, let me say something. Sometimes I don't even to understand these things, like when you check different books, they have so many different things to say sometimes, right? Because according to them, here in this book, they are saying that the word done here is going to be positive, right? It's going to be positive and not negative, right? They say that obviously let's look at back at A. It says that positive work is being done by the gas since the gas is expanding, right? We understand all of that. I am so concerned sometimes when it comes down to the different books and so forth that they give you different information sometimes. You don't even know which one to trust, right? Honestly. Yeah, I mean, I don't really, I hate when they have different information all over the place, to be honest, because it makes your life a little bit much harder now. Mm. Anyways, the answer to that question, the last question, right, would be linked to the fact that um, because you're expanding the gas, it means that you will require heat to expand the gas, right? So if I'm expanding my gas to that amount, right, to 5 centimeters to 5 meters cube, then it means that the work that is done to expand the gas is equal to the heat that is added to the gas. So in a sense, our internal energy, right, will be increased by the same amount of work that was done. So in a sense, our total internal energy should be double the amount of the, well, not say double the amount, yeah, basically double the amount, because the work that is done, right, is I think it's 600,000, right? And we're saying here that the same amount of heat would have to be applied to expand the gas, right? So overall, our internal energy is going to be the sum of that, right? Well, not necessarily the sum of it. Yeah, it's going to be the sum of it. But remember, we are working with the information that says that the work is negative, right? So I think the internal energy might be zero, but I don't like when you're checking different books and they're giving you different information, to be honest, right? So that just kind of make life a little bit harder. Right. Anyways, here's another question. right? So as you can see now, with this is generally the type of questions that you can get with the graph looking like this and all of that, right? So it says that a fixed mass of an ideal gas is pumped. All right, well, let me say that again. Right, so a fixed mass of an ideal gas in a heat pump undergoes a cycle of changes of pressure, volume, and temperature as shown in the figure. It says that it's not drawn to scale. It says that no heat is supplied to the gas from A to B and from C to B. It says here that the increase in the internal energy of the gas is as shown. So from A to B, my internal energy is going to be 1,300 joules. From B to C, my internal energy is going to be minus 1,200, which just shows us that the heat that you're losing heat. And I'll show you why, and I'll explain to you why. From C to D, so this is from C to D here, so from C to D, it is also losing temperature, or losing heat. So they said it's minus. It says that using the first law of thermodynamics and the data supplied, it says that determine the following. The first thing they want us to do is to determine the work done, right, on the gas from A to B and basically the work done from C to D. Let's see if we can do that. So WAB, right, is going to be equal to, let's see here, pressure times change in volume. Let's see, right. In this case, how we should go about doing this, in a sense, let me see here, give me a second. Okay. Oh boy. Give me a second, guys. All right. So we can just simply go ahead and use so we're not going to use this because it's going to be a little bit more harder to use that. What we can do is to use the overall first law thermodynamics equation that says that U is equal to Q plus W. We want to find W, so we just transpose. So W will be equal to U minus Q. Now, the question had said that there's no heat supplied to the system at A to B. So what that tells us is that Q is going to equal to 0, right? So my internal energy, which they stated to us from A to B, is 1,300 joules. So the work done in this case, right, to move from A to B, right, is going to be this amount, 1,300 300 joules. All right. I've less than a minute, so I'll restart it to just finish up these questions here. Okay. So we'll just do the same thing for C to D, right? In this case, we're seeing that the work is going to be negative, and it makes sense because you're moving from C, which is here. So the first one, I'll explain the first one again, right? So imagine that, you know, you're moving from A to B, right? With this, you're basically doing work on the gas. The reason why you're doing work on the gas is because the volume of the gas is decreasing, right? So basically, you're compressing the gas. So moving from A to B, you're compressing the gas. So what we're seeing here is that the question said that no heat was supplied to the gas from A to B. So there's no heat. So if there's no heat, then we can use the thermodynamics equation, right? Or the first law of thermodynamics. We got the internal energy from A to B, which is 1300, which is, you know, the internal energy, of course. So by way of just manipulating the equation or transposing it to make the work become the subject, it shows us that the work is equal to the internal energy minus the heat. Heat is equal to 0, so in a sense, my work is equal to my internal energy. All right? And I expect that the work is going to be positive because you're doing work on the gas, right? When we look at C to D, the gas is expanding, which means that the work should really be negative, right? So that's how we can see now that the work here from C to D pans out to be minus 450 joules because of what is happening to the gas at that point. Right? No. The question continues. It says to us that we should find the heat supplied. Let me see if I answered everything correctly. Give me a second here. Oh, so for II, they want us to find the work done, right, from B to C. No, the work done from B to C. From B to C. Remember now, what type of condition is that, or what kind of process is B to C? B to C is right here.
So is that the volumetric, the isovolumetric?
Yes, the isovolumetric. So with that being said, pressure times change in volume, of course, is going to equal to 0. So the work in this case from B to C is going to be, yes, Patterson, isochromic or isovolumetric. So the work is going to be equal to 0 right now, right there and then. Now from D to A, right, we expect the same result. We expect the same thing. So for the work done from D to A is still going to equal to 0 joules, right? Now if they go and ask us what is the heat supplied to the gas from B to C, right? We got the internal energy from B to C. So all we just need to use now is our equation for the first law of thermodynamics. So Q would be equal to, and this is Q from B to C. So when I transpose that equation, I should get that internal energy minus the work is equal to the heat energy. In this case, the work is equal to 0, of course. We know the internal energy. So that internal energy is minus 1200 joules minus 0. So in essence, from B to C, I expect to be losing heat, and it makes sense because if I'm decreasing pressure, so at B my pressure was 20,000 times, well, yeah, 20,000, right? That would have decreased to 11,000. So that goes to show that I think I'm saying it incorrect, but let's just say, 200,000. This is 200,000, and then it decreased to 1100,000. I don't even know if I'm saying it correctly, but in a sense, because your pressure is decreasing, right? That in a sense shows us that we're losing heat. So by way of just working this out, we show that the amount of heat that we lost is this amount, right, during that process. Fair enough? Question continues, and it says that the increase in the internal energy of the gas from D to A, right? D to A. Let's see here, increase in internal energy. So let's see. All right. From D to A. We know that the work is equal to 0.
Sir,
Yes, go ahead.
I cannot see what you have below the QBC equal U minus W.
Okay, so it is QBC is equal to minus 1200 joules minus 0. So QBC is equal to minus.
Thank you, sir.
Yeah, man. Now this part looks a little bit tricky now, right? To find the internal energy. Internal energy, all right. All right, maybe they're using something else that I might not be aware of. We don't get anything about temperature. Right, give me a second here to see if I can look it up and see what's going on. Internal energy. I hate this book so badly, right? This study guide is I don't know if the updated version have the corrections made in it, but the one that I'm looking out of, it clearly have some incorrect stuff inside of it, right? But we're not gonna stress that. Let's see here. That it wants us to find the internal energy. Okay. So it says that all these internal energy values should be added up to 0 because the change in internal energy from A to A is 0. All right, cool. So in order for us to find that change in internal energy, based on what that book is saying, right? Let me just kind of clear up this a little, right? Now, what they're saying, we start at A, right? We travel from A, we go to B, we travel from B, go to C, travel from C, go back to D, and then we would go back to A. What they're saying here is that the internal energy from A to A must be equal to 0, right? So if I want to find the internal energy from B to A, then what I am going to do is to add up all of the internal energies right? And obviously that is going to be equal to 0. And in that process, I can then find out what BC is going to be. So let's just look at it here. So from A to B, we know the internal energy. So that is 1300 joules. Plus B to C, that is minus 1200. Good? Then from C to B, to D rather, that gave us, we're going to add it, so that's minus 450 joules. Now, I'm going to add to my internal energy from D to A, all of this must equal to 0. So when I add up all of this over here, so, and just basically make the internal energy from D to A becomes the subject, then I will find out what that amount of internal energy is, because we said that the overall change in internal energy from A to A must equals to 0, right? So when we do the math, right, 1300 minus 1200, that gives me 100. 100 minus 450, I'm going to get negative 350. So in essence, right? So in essence, we're saying that the internal energy from D to A, right, is going to equal to minus, well, is it minus? It's positive 350 joules. Positive 350 joules. So in essence, what you could have started out with is to say that the internal energy from A to B plus the internal energy from B to C plus the internal energy from B to C, right? Am I saying that correctly? No. From C to D now. C to D, right, plus UDA is equal to 0. So in a sense, that is something that you must remember, to say that in the entire system, once the system is connected to each other, where it's a cycle going back and forth, right, then the overall change in the internal energy must be equal to 0. So if I know the internal energy now at D to A, I think I can find the heat supplied to the gas from D to A. Remember, we said that at D to A, the work is equal to 0. So in essence, my internal energy, right? My internal energy from D to A is going to equal to the heat added to the system, or heat supplied to the system. So in essence, Q at D to A is going to equal to 350 joules. Right? Okay. All right. I'm sure they did not give us a temperature. right? Did they give us a temperature? I'm not. Okay, yes, 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 yes. They gave us the temperature values. That's a lie. So these things right here are the temperature values. Now the question continues, right? And it asks us to find the number of moles. Cool. So I was looking a while ago to find out whether or not they gave us a temperature value, but yes, they did give us temperature value at the specific point. So what we want to do now is to find the number of moles. In order for us to find the number of moles, we must use an equation that links number of moles, and that is going to equal to PV is equal to nRT, right? So I can just consider one location possibly. Let's just imagine what is happening at B, because it's the same number of moles that is going to be at B, that's going to be at C, that's going to be at A, it's going to be at D. So I can choose it at any point. Once I can read the pressure, once I can read the volume, then I should be correct. I should be fine. So let's just transpose to make N become the subject. When N becomes the subject, we have P times V divided by N, my bad, divided by R times T. So N is equal to P times V divided by RT, right? So we're using the point at B. So my pressure at that point is 20 times 10 to the 5 times that particular volume, which is 0.42 times 10 to the minus 3. Divide that by R, which is our molar gas constant, which I think is what, 8.31, times the temperature, which is 919 kelvins. So let's just try work that out and see what we're getting. So 20 e to the 5 times 0.42 e to the minus 3. The numerator gives me 840. I'll divide that now. So 8.31 times 919, I get 7,636.89. When I divide up these numbers now, I'm getting that the number of moles, N, is equal to 0.11 moles. So that's the number of moles that is basically present in that particular gas. Right? If you agree, let me know. If you disagree, let me know.
Sir,
Yes, go ahead, please.
why did you choose 919 Kelvin?
Yes, because remember now, as I said, you can use any specific points, right? Because that's the temperature associated with this pressure. So when the gas is at this pressure, the temperature is 999 Kelvin, 919 Kelvin. Because remember,
Also, if I chose the 2.5 times 10 to the 5, I would have to use the 492.
yes, because yeah, it would correspond to that temperature.
Okay, sure.
Mm-hmm. Yeah, man. This is what the chat is saying here. All right, good, 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 good. Any other questions? So remember that the mole is not going to change regardless of the fact that the pressure is changing or the temperature is changing. All right. So if there are no questions, then I think we can end it here. Now, please, I'm gonna ask you guys to start reading up on what we call molar heat capacity. Right? It's nothing hard. It's quite similar to that of when you were trying to find the heat capacity of maybe, you know, of water and all of that kind of thing. Right? When it comes down to molar heat capacity, we have been talking about the equation that says U is equal to Q plus um plus W. But where is this Q coming from? How can we find this Q? Now you're going to realize that Q, which is the heat supplied to the system, right? We can then find what we call the we can find the heat using what we call the formula here that says N C times, I think it's the temperature, I believe. I don't remember it exactly, but we're going to introduce this formula eventually, right? Where we can pretty much find the heat that is added to the system, right? You know, when if we compare the equation that we know of when we're trying to find the heat capacity or something, or the specific heat capacity, you would say Q is equal to MC times the change in temperature. In whenever we're dealing with the gases and we're trying to find the heat, we don't use the mass of the gas, but we use the mole. So in rather than using the mass, we say that Q is equal to NC times T, right? But that is something that we'll talk about in our subsequent lesson, right? So that's about it then, right? So let's read up that information. I'm going to probably send this PowerPoint with all the stuff written in it and all of that. But that's it though. Submit your name for me in the WhatsApp group, all right?